Thanks for being here today. And for those who joined us yesterday, who is that, by the way? Can you raise your hand? Okay, so many of you have seen driverless AI, so I can keep it a little bit brief with a general introduction. Just want to point you back to the roadmap. So it's in flux. If you have something to say about, you want 3D distribution for insurance, we would love to add that. Help us shape the roadmap. You've seen that the product has come along nicely in the past year and a half or so, a little bit less than a year and a half actually. The general availability was made last November or so, October, November. So it's only about a year old, and we've already added a lot of features, but still we have no multi-node, for example, and we can't yet handle terabytes of data. It's only tens of gigabytes. If you're lucky, maybe 100 gigabytes, 200 gigabytes of data. And we're adding features to make it better. For example, data table will be used internally for the data manipulation more and more. We already are using data table, the Python version. We'll add more things like algorithms that are scalable for streaming operations, so something like follow the regularized leader or deep learning, mini batch streaming, where any size can be processed. But of course, at that point, you are sacrificing something versus something else, right? There's no free lunch at a terabyte. Not many can do full Kaggle Grandmaster style feature engineering on a terabyte today. And our mission is to do that. So give us another year and we'll be there. In the meantime, we're doing full Kaggle Grandmaster style feature engineering on a few gigabytes, tens of gigabytes, maybe 100 gigabytes. And on that scale, we can do super hardcore data science and stacking and all that. And at the same time doing this on a single box so it's manageable. And the scale up is done with GPUs or multiple Xeons or so, CPUs, whatever you have. So we're using all the cores of the machine. It's as parallelized as it can be. And the features we have are basically IID data sets. So that's standard data sets where random shuffling is okay. Then there's data sets that have time series components in them, where you have to tell us what is the axis on time. Now you can't say, I don't know what the axis and time is, you figured it out. Automatic mode actually works. And today you can say basically just figure it out, and it will find out if it's time series or not. But as you know, it's not that easy, right? If it's half IID, half time series, it's a little bit of time series, but not strongly seasonal, for example. It's like collected, I don't know, t-shirt sizes over the last 50 years. The t-shirts are getting bigger and bigger, right? But it's not really seasonal, it's just a trend. So these little details, we still have to work out a recipe that's really good at doing these next level improvements on time series. For version 1.4 that we announced today, by the way, so you see here, this is the announcement that came out in the product. So for those of you who have driverless AI, you can click on notifications in the top and you'll see this announcement. So there were lots of little improvements we made this last month, and all together they stack up nicely to just make time series better, to make big data better, to be more interpretable, especially for time series. And I will show you some of these things in a live demo soon. But let's make sure we cover the main points. So LightGBM, for those who don't know, is an algorithm by Microsoft. It's a gradient boosting algorithm like H2O-GBM, like XGBoost. It's an algorithm that runs on CPUs or GPUs, and it's highly optimized for low memory footprint and speed. And it's doing just that, and it's helping us to make better models in an ensemble or alone, as the only single model. And also we have a full Mojo support for it, which means that if you have a LightGBM model in your pipeline here in driverless AI, and you export that final pipeline as a standalone Java pipeline, then that will do the full LightGBM scoring, just like LightGBM itself in C++. So we have a Java version of the LightGBM runtime if you want. It's also actually used as the new default model if you have a larger data set than a certain size. So especially when you have GPUs, you're limited in memory, and you only have, say, 16 gigabytes of GPU memory. XGBoost would have run out of memory sooner than LightGBM, so we automatically switch to LightGBM. And if that's not enough, we'll automatically switch back to CPU. And if you have a few hundred gigabytes on your box, then you can pretty much solve any size problem that would be reasonable to put into driverless. So there should be no limitation on the scalability right now except for your memory on your system and the time you're willing to wait. Because driverless is still meant to be an iterative solution that keeps doing models and features and models and features until it converges and finds a good pipeline. It's not meant to train one model, right? So what we do internally is we subsample first. So let's say you turn the knobs to a certain setting and you give us 100 gigabytes. What happens is we first downsample to a few million rows, and we do the genetic algorithm, the feature evolution, the particle swarm, the Monte Carlo, all these techniques are running on a smaller sample. And we figure out what interactions matter, this column, target encoding, or binning, or clustering. And once we know what to do, then we do it on the full data set. Depending on the accuracy settings, it might also be a sample. If you set the accuracy to 1, you're not going to get a model on the full 100 gigabytes because you said you wanted an accuracy 1, right? So there's a way to basically tune what you're getting. And one of the nice things of the product is that it tells you that in advance. So while you're setting it up, here I have a data set that's 3 gigabytes, 23 or so million rows. You can look at the data set. I see the distribution of the columns. Every column has a distribution. Oops, and I can visualize it. And I see the outliers on that data set. Oh, interesting. Ordinal UPB has 4 outliers here, right? 4 points. And each point could be multiple points if they're close together. But in this case, it was really just one outlier at that point here. So this is a nice use of AutoViz to just quickly give you a sanity check of the data. And maybe you missed something. Maybe there really is something you didn't know. It tells you where's the what distribution the columns have, and also where are the missing values. So you can quickly see, oh, there's something that I don't understand, doesn't make sense. This column should not have a single missing value, for example, but it does have some. So this is part of the base H2O driverless AI. However, AutoViz got faster in this version, 1.4. And you might not notice much of a difference, but at least you see here there's a menu at the top, AutoViz. It shows you all the visualizations that were made. So you can launch a visualization, and you can come back to it later and see it again, just to see how long it took and what you did visualize or not. It's just nice. It basically can run in the background. When you start the visualization, you don't have to wait until it's done spinning. You can just do some other experiment and come back to it. So this 3 gigabyte file took a minute to visualize, and now it's of course cached, and you can see just the skewed distributions. So AutoViz got faster. MLI also has nice improvements. Actually, let me show you one on a time series problem. So time series, all you have to do is run something where the time column is set, right? So the time column, where is it here? The time column I had to set to something that's not off. By default, it's off. But you can set it to auto, in which case it will take the best time column that we can find. Or you can set it to a date, for an example. In this case, where you know there's one date column, you can help us, just tell us which one it is. But if there's only one, you don't actually have to help us. We'll find it automatically. And if there's multiple time columns, we'll take the one with the biggest span, or the one that makes the most sense. I think there's some heuristics in there. Let us know if it doesn't automatically find the right time column. We would be interested in seeing how we can improve. So in this case, it found out that the exponential weighted moving average of different lags of the sales per store and department for Walmart were predictive. So if you group in a tree model, if you make a feature that says these are my past sales, right? And this is the exponential weighted moving average of my past sales of a year ago, 2 years ago, and so on, or 16 weeks ago, or 55 weeks ago, whatever the numbers say here. If you put those numbers together, and that is my value, and other stores, other departments have similar values, then that's a good feature for the tree to split on, to say, oh, the stores with a big sales number over those periods of time, they go into this side of the tree. and the stores with a smaller number go this side. So that's how you have to think. So this is how we do time series, right? We make these tree-based models that are looking at those features that we make based on historic information. And now you wonder, how well is this doing? Well, this was a small data set that I ran for only like a minute or two. But when you do interpretation for this model, you can actually see this is the R square over time, which is telling you if it's 0, it's totally not good, and if it's 1, it's a good fit. So this is actual versus predicted correlation, roughly speaking, Pearson correlation. So you can see at the very beginning it's bad because we are not supposed to, by the way, make predictions on the training time. This is just used to see how good was the fit. And because we have a forecast horizon of this length here, of the yellow block, that's the test set. That's where we make prediction into the future, where we can see, by the way, that we get a little bit worse over time, right? Because it was only good at the beginning, and then it goes into the future where you get worse and worse. So now you have a good estimate of how bad the predictions are in the future. And in the past, the fit is pretty good. It kind of memorized everything, except for in the very beginning where you don't have lags that go back 30 weeks or so, because we are saying we need to be able to predict for 30 weeks into the future. And in order to predict 30 weeks into the future, at that future point in time, you have to be able to look back 30 weeks into the training data. And that is not possible for the beginning of the data here. So that's why it's flatlining at the left side. It's just predicting some kind of a mean number. And don't worry about it's negative, it's not great. We apologize. This is early work, basically. This is still doing a prototype of how would you do diagnostics on time series, right? And you could argue, I don't want to see predictions into my past, into my training data, because I have the actual values. Why should I look at predictions? But it still helps you to get a feeling for how well was the model able to capture those effects. So I would say, look at this piece here, and then maybe the end here where it falls off, to get a judgment of how good it is. And here it makes even combinations of departments and stores that the model found automatically that these groups are important for time series, so that each group of department and store has its individual time series, right? A Minnesota food section is different than a Chicago kitchen section in the store. So you can't compare these sales in one time series. You have to make a separate time series for each. And driverless AI automatically finds those time groups. And in this case, you can say, for example, store 21 and department 3 had a reasonably good prediction, but it's still only a 0.5 R squared. So it's not great, but here you can see, okay, it at least got the spike right, the timing roughly just was off with the scale. And that's because it's small data, and I aborted the model very early. And now I can see, okay, I understand it's not the best prediction. And this was one of the better ones. Let's look at 530. That was the worst prediction there in the table. And you can see, okay, it should have been a different version. And you can see here, actual predicted is totally off, right? It should have been 400, but it predicted 24. So now you can maybe see what's wrong with this store or department, and that's model diagnosis, model debugging, model interpretation, if you want. But interpretation really only shows up once you do click on a point. Because at this point in time, you can now see why exactly we predicted this number. And here are the Shapley values. So these are the contributions to this very prediction for this store and department at this time. Why did we say this much? And you can see each feature, even though these features are complicated, well, these are the lag features that we made to give to the algorithm. For each feature now, we have a contribution to the overall prediction. So if you add them up, they will add up to the sales number we predicted, up to the bias term, which is a constant. So just to give you some idea, this is the new time series MLI, which is brand new, and we love your feedback. This is alpha. It's not like meant to be the final version, right? This just came out, and we would love your feedback on that. It's not easy to do interpretation of time series in general, and this is an attempt to do just that. Now, light GBM, as I mentioned, if you have light GBM and you say, let's see, can we use it somehow for this data set? So I predict a
I don't know what I want to predict, maybe whether or not this account will be delinquent. And that's 23 million rows. And now it will make a preview on the left side that says, this is how long it will take. It says it will take hours. It says it uses 1 million rows for the feature evolution sample size per fold. So what this means is, as we can see, feature evolution is light GBM, and it does 4-fold cross-validation. So we take the 23 million rows, we cut it into 4 folds, and each fold is now a few million rows, right? 5 million or so. And then we say, no, don't do 5, just do 1 million. That's the maximum we want to do for each fold. So then it will do 4-fold, and each of the 4 folds will take no more than 1 million rows. And that will help us do faster feature evolution. So where it figures out what interactions to use and so on, it does it on that sample. So it's more than 1 million rows total, but each fold is 1 million. Now if you say I don't want folds, you can turn down the accuracy, and at some point it will say, I will only do maybe 1/3 validation split, see? And now that it says 1/3 validation split, if you can't read it, I'm sorry, I can't zoom this. This is, every time you zoom in, it goes back down. Like it wants to look good, basically. It doesn't let you screw up the layout. So the 1/3 validation split on the 23 million would basically mean you cut off like 8 million or so, right? And 8 million holdout is great, but you really don't need that much. So we still will downsample both the training, the 16 million, and the 8 million. And in this case, we'll actually downsample to 200,000 rows because you set the accuracy to 5. So this will make it much faster. And that's basically some of the improvements now. You have light GBM, you have GLM, you have XGBoost, and then under the expert settings, you can enable all of them, right? You can have light GBM on, and you can say I want XGBoost off, or you want Tensorflow on. These are all first-class citizens. Tensorflow still does not have a Mojo yet because Tensorflow wants to live in C++, for which a Mojo is coming in a few months or even earlier. But Java has full support for everything but TensorFlow and RuleFit. RuleFit is also going to get revamped, so that's the two that say alpha. Those don't yet have a Mojo, but they do have a Python scoring wheel. So if you're okay with batch scoring in Python, everything will work that you see here, everything. All right, so basically I covered these points here. We have also, checkpointing and feature brain. That's a nice innovation. That is basically saying, if you run an experiment over and over again on your same data set, please get smarter. Don't start from scratch every single time. That's a nice feature that will help you get better accuracy over time. And another one is that the time series also does multiple windows, rolling windows. So you don't just have one holdout, but you might have multiple holdouts. So that helps you get a better model. And one tiny little thing that I'm proud of is we detect the date stamp format in the preview. So you can see whether your date is properly recognized by driverless. And you see the format string, year, month, day, and so on. You see the min and max of the range of the dates. And that is a nice, quick sanity check for your time columns. So if you have any questions, now would be a good time.
Yeah. So we have a question.
Mm-hmm. Maybe I can just...
Hello? So I can bring him up
Thanks.
to you.
Yeah, perfect. Yes, the question is, are ideas from the reusable holdout paper used in driverless AI? Yes, they are. We are actually doing multiple repeated samples and then scoring those and seeing if the distribution is shifting or not, if it gets a significant change. So we're not overfitting on one test set by scoring it over and over again, or validation set, as we call that piece that we use for the training process to make better models. How much does it matter when you change the accuracy settings? So yes, it's a good one. That's why you look at the preview. When you turn the knobs, always look what happens in the preview on the left side. That's what will tell you what's going on. And there's really just, our defaults are a good guess. That's a good starting point, but you really should be encouraged to turn the knobs and see how it behaves. It's all relative, so you can't have everything. Obviously, you want highest accuracy and highest speed and the most interpretability, it's not going to do that, right? It's going to prioritize accordingly. So if you say I want highest accuracy, it will do more cross-validation. If you turn the interpretability up, it will do less feature engineering. So it will do a super cross-validated model, but it won't change much in the features. So it's going to converge faster at some point. It will find the best parameters and be done. So the time 10 might not actually be used because it will stop early because there's nothing to do. So you can basically turn up the time as long as you want. If the experiment cannot improve, it will stop at some point. And of course, the more time you give, the longer it will take before it will flatline and say, I'm done. It might still try something else. So it's all reasonable, basically. All the knobs mean something to us. No matter how you turn them, we always listen to you. It's not ignored. But the exact outcome is dependent on the case. And another question was, do we do spatial cross-validation? I'm not sure exactly what you mean, but the cross-validation time series is causal. So it's always a past to train and the future to test. And ideally, the test is separated from train, just like the actual test is separated from train. So if you have a 2-day gap between modeling and going to production, that 2-day gap is mimicked in the scoring, in the training and model tuning piece. And if you have multiple such windows, they all will have that same splitting so that it mimics the actual test set deployment. And we don't have geospatial feature engineering yet, if that was the question. So if you have longitude, latitude features, those are just strings to us right now, purely categorical strings, so that they're kind of ignored.
Quick question, can you define your own folds?
Yes, there is a fold column support.
Okay. Can you repeat the question for the
Yes, the question was, can you make your own folds? And that actually is a very good question. And the answer is definitely yes. There is a fold column here. You can provide your own folds, and you can say, let's say I have 5 types of people, and I want to have each one in its own, in the test or in the train or in the validation, like that. They should not be mixed up, basically. And you can say, separate cities, right? You train on San Francisco and New York, and you hold out Chicago or something like that. So you can make your own fold column. You can make your own weight column, and you can also make your own time column. And we do now have automatic dropping of features that are drifting between train and test and validation. So let's say the interest rate is changing slightly over time, and you have a model that trains that and then memorizes interest rate, and that is a proxy for the outcome in a way, because interest rate is correlated with the outcome that also changes over time. And you don't want that. You want a model that is not like cheating that way, so it automatically drops certain things that are shifting too much, so that the model is truly generalizing on features that have a similar distribution in train and in testing. So that's another feature we added to avoid overfitting.
So Arno, do you mind if Eric gets set up while you take one more question?
Great, that's a good idea. Actually, I think we ran out of all ideas, so Erin is next, our chief.